Hello guys, good evening everyone. It's nice to meet all of you. I think this was the first session that we're doing, unfortunately. It's been a little bit delayed. So I think we have quite a few students here. Let me just, if you have any questions, please feel free to ask me. Okay. I would like to keep it truly interactive. So Sarala, Sanjeev, Ganesh, any one of you, if you have any questions, please let me know. I don't want it to be a one-way conversation. So it can be any questions related to the course, or it can be some general questions related to semiconductor devices, right? Why are we studying the semiconductor devices and so on? So I'm pretty open to the questions.
Good evening, sir.
Good evening, Sanjay.
Good evening, sir. Sir, depletion, application or inversion, something doubt, sir.
Okay, fine. Sanjeev, so depletion in a PN junction, समझते हैं आप? Hello? Depletion region in a PN junction? Are we sure?
Yes, sir. Yes, sir.
So let me ask you one question, okay? I mean, सवाल पूछता हूँ मैं.
Sir, N-type भी depletion, नहीं, N-type happy.
हाँ.
Sorry, sir.
NMOS device में ना, NMOS device में आपको समझना है कि depletion versus inversion, right? Correct? यही है क्या आपका question?
Yes, sir. Yes, sir.
ठीक है, okay. So before we do that, when इससे जाने से पहले हम basically PN junction को समझते हैं, ठीक है? एक मिनट review कर लेते हैं, okay? This is a PN junction, right? A device like this. There's a P region, there is an N region, and in between there is a depletion region. You know, why is this depletion region formed?
Is this working? Is this working?
Yeah, why is this depletion region formed? Jeet?
Due to the oxide, sir.
Sorry, due to the?
Oxide.
I'm sorry, I'm not able to understand. Due to the? This is P-type, right? P, lots of holes are there here, excess holes are there. And on the other side, you have excess electrons, right? So because of this, there's a diffusion of carriers from holes from the P-type to N-type, and similarly electrons from N-type to P-type, right? So when they diffuse, these are free carriers. Electrons and holes are free carriers. Means they can freely move around in the lattice. But when they move into a different region, they leave behind an exposed, right? When they move, they leave behind ionized donors or acceptors, right? This is clear. Why is this? Think of a lattice, a silicon. Let's take a N-type. So arsenic atom. This is basically, right? You have a silicon lattice. In that, one of the silicon atoms has been replaced by an arsenic atom, right? Arsenic is an N-type impurity. This is an N-type impurity. Now, arsenic has 5 electrons, correct? 5 electrons in the valence shell. Out of these 5 electrons, 4 are part of the lattice, correct? There is 1 electron here, 1 electron here, 1 electron here, 1 electron here from this side. And from the silicon atom, there will be 1 more electron. So you have a satisfied valence of 8, so there is a stable bonding. But there's an additional electron in arsenic here. This is an additional electron which is free to move around. So this particular electron can move around. When it moves around, when electron goes away, you get arsenic. Basically becomes an arsenic ionized arsenic plus. Similarly, instead of arsenic, if you have a P-type impurity, let's say a boron, when you remove an electron, this is plus electron. This will be boron minus plus a hole. These are what we call as ionized donors or acceptors. Now, because of this, when you have a charge, this particular region, these charges cannot move. These ionized acceptors or donors, they are fixed. They are fixed. We call them space charge or fixed charge or whatever, right? These are space charge region or depletion charge. Depletion charge. Right? This is how a depletion region forms in a PN junction. 1 second. Sanjeev, is it okay till this much? This far? Sanjeev? How a depletion region forms?
Yes, sir. Yes, sir.
Okay, good. So now, the question you had was on how a depletion region is formed in a NMOS capacitor, correct? An NMOS
Yes,
capacitor
sir. Yes, sir.
has a P-type semiconductor like this. There is a P-type semiconductor, and then on top of it, you have an oxide, and then there is a metal on top. This is metal, and this is oxide, correct? Now, P-type semiconductor, let's assume that I'll apply a gate voltage, VG, which is positive. Let's say 1 volt, just for example. VG equal to 1 volt, positive. Now, what happens to the substrate? There are lots of holes here, right? This is a P-type semiconductor means lots of holes are there in this, all over. Now, when you apply voltage on the metal gate, this oxide is an insulator, and essentially it will repel the holes away from the interface. Do you agree? Agree?
Yes, sir.
Yeah, good. So now when it repels, what do you have left behind? There is a negative charge or a positive charge. When you move away holes, what is left behind?
Positive, sir.
Negative charge. Very good. So basically you have lots of negative charge here, just under the gate.
Should I press this green button?
Okay. So this is basically a depletion region. Understood? Because this region under the gate, okay, region under gate is depleted of free carriers. Agreed? So this is different from PN junction. In PN junction, we had P-type and N-type in contact. Right? But here, you have an oxide in between.
I will cut this because I cannot open it. See, stuck.
So, in this case, if I have to draw the space charge region, space charge, what you will have
See,
is,
this is here. I cannot place it inside the flow.
we have, let's call this as 0, and this I'll call as minus Tx. This thickness of the oxide, I'll call it as Tox. Okay, and then there is depletion region. So now, if I draw the space charge profile, there will be a negative charge in the semiconductor. This is my width of the depletion region. Okay, on this side, I have a positive charge. This is the interface. Agreed? So this is how the charge will look like. Sanjay?
Yes, sir.
Good. Now, what will happen if you have a depletion region like this? That's the question. Why is the inversion formed? Will the inversion form if you have a depletion region always like this? Yeah. Yeah. Why does the inversion form?
Opposite, sir.
It's not opposite. No, it's only depletion. No. The charge density is fixed here. How much is the charge density here? Total charge here. This is my depletion width, right? The total charge here is going to be Q negative, Q minus, equal to Q times Na times W depletion. This is the amount of charge. This is not inversion charge. Okay, this is not, this is space charge, not inversion charge. Inversion charge also is negative, but it is free to move around, right? Or at least electrons, correct?
Yes, sir.
So why does the inversion charge come about if you have a depletion region? Remember, always your semiconductor wants to be in equilibrium. Now, when you create a depletion region like this, you are pushing the semiconductor out of equilibrium. Then what it does is it tries to produce electron hole pairs. Okay. So in this case, electron hole pairs, okay, are produced to restore equilibrium. If you have excess of carriers, you have recombination. If you have depletion of charges, you'll have generation of electron hole pairs. Is this clear, the concept? Now the question is, what will be the direction of the field? Okay, direction of the field is always from positive to negative. So the electric field in this case will be in this direction. This electric field causes the holes to move away from the interface and the electrons to come near the interface. Correct? If you have an electric field in this direction, it is positive. That means holes will go away from the interface here, and electrons which are produced in the electron hole by the generation will come near the interface, and they form a inversion charge at the interface. This is my electrons. Sorry. Electrons produced. Electrons produced due to EHP generation. Right? This is inversion charge, we call it. Agreed? This is different from the traditional fixed charge. Okay? This is occurring only at the interface. Yes. Yeah. I'm sorry, somebody else is speaking. Can you tell me what? Sanjeev, I think.
Yes.
Who is speaking? I'm sorry, I cannot hear you clearly. Can you type in the chat box? Yeah. Guys, the TS, anybody speaking? I don't know who is speaking. Yeah. Any questions from so far, whatever I have talked about?
About holes, sir.
About holes? What is the question?
Sanjeev is speaking, sir. Sanjeev Karji.
How produce holes, sir?
Okay. Okay. So what happens is, okay, then we have to go back to the basic semiconductor. Okay, just take a piece of silicon. Okay. Now, if you have a silicon, let's take intrinsic silicon. Okay, simpler. Intrinsic silicon is without any dopants. What is the number of electrons and holes in this? What's the number of electrons and holes in this?
2, sir.
Huh?
Silicon 2, sir.
No. N is equal to P equal to Ni, right? Is equal to 1.5 into 10 power 10 per centimeter cube, isn't it?
Yes, sir. Yes, sir.
Correct. Why is this number 1.5? Why is this 1.5? Why is this 1.5?
I cannot remember, sir.
Okay,
Now.
good. So no problem. So what happens is, if you have a perfect semiconductor at T equal to 0 Kelvin. N equal to P equal to 0. There are no free electrons, there are no free holes. When you have temperature to be 0 degrees. Okay. Only when you have only when you have a certain amount of temperature, this becomes different. What is the difference? As you increase temperature, the bonds will break. Okay. And when these bonds break,
Yes, sir.
you have electrons and holes created. Okay. Okay.
Yes, sir.
In the
Yes,
silicon
sir. Okay.
lattice, in your silicon lattice, Si, you have like this, right? Lattice. Initially, at perfect 0 degrees Kelvin, there is no bond breaking. But as the temperature increases, some of these bonds break. What do you mean by bonds? Every bond is simply a pair of electrons. Okay, there are two electrons which are shared between silicon atom. This is essentially what we call as a bond. When a bond breaks, you have an electron which can freely move around in the lattice and a hole which is left behind. Okay, so basically bond breaking leads to electron hole pair generation. Okay.
Sir,
So
if
electrons and holes.
bond, if bond is breaking,
Hmm.
breaking, then holes come.
Correct. There is a hole produced, and then there is an electron which is free to move around in the lattice. Okay. Exactly. Followed? So you'll always have a couple. Now, what happens is, in this case, you created a depletion region. When you have a depletion region, semiconductor always wants to come back to equilibrium. What is the equilibrium carrier density here? N equal to something. In this case, it's a p-type semiconductor. Let's assume that it's 10 power 17 doping concentration. So N is going to be 10 power 3, P is equal to 10 power 17. It wants to come back to this equilibrium number. But a depletion region does not have any of these charge carriers. So it generates electron hole pairs till you reach this equilibrium. Follow? But then, whenever that kind of whenever the electrons and holes are produced, holes immediately move into the substrate, electrons come to the interface. Because the electric field is positive here. Okay? Agree?
Okay, sir.
Yeah. That's why you have the generation of inversion charge. All right?
All right, sir.
Yeah. Any other questions, guys? Nandana? Any question from the Excel sheet you want to check? Can you read one question?
Because he broke on it, so I don't need it.
Sanjeev asked about threshold voltages.
Threshold voltages. Okay. That's interesting, right? So basically, what is a voltage required to produce this? Okay, first of all, we have to define for threshold. What is the definition of threshold? I hope it's a threshold in the context of MOS caps. Okay, that's what I'm answering here. What is the definition of threshold voltage? If you have a p-type substrate with Na equal to 10 power 17, I want to have, in a regular situation, P equal to 10 power 17 here, N equal to 10 power 3. Correct? I'm dropping the units. You assume that the units are same. You know, we know what it is, right? Per centimeter cube, per centimeter cube, right? This is always the units are given. Okay. So now, this is regular situation. A bulk semiconductor has this carrier concentration. But suppose you invert the semiconductor, like what we did in this case, no? This diagram. We have done inversion of this semiconductor. Right? This is an inversion of semiconductor. Let me get rid of this and this. Okay. Now, threshold means this electron density. Density should be equal to how much? 10 power 70. Follow? So, if you have the inversion charge as much as the bulk majority carrier charge, majority carrier concentration, then we have inversion. So, it's actually much more than inversion in this picture, the way I'm drawing it. So, shall we do this? Okay, this much. This is my inversion, right? Exactly equal to the bulk charge.
So, threshold voltage only for inversion.
Sorry?
So, threshold voltage only for inversion
No.
regions.
No. I mean, you can also define a threshold voltage for a diode where there is no inversion. If you have a PN junction, this is a threshold voltage in the context of MOS capacitors. Okay. But if you have a PN junction, when you draw the IB of a PN junction, you draw it like this. Correct? Where there is a linear region, you extrapolate and then say that there is a VT. Okay. This is your VT, above which the current significantly increases, right? This is a threshold voltage in the context of diode. Threshold is basically a kind of a limit after which the behavior changes. That is the definition of a threshold. Okay? Is this clear?
Okay, sir.
Yeah. Okay, good. Anybody else? Jeet? I believe Jeet asked a few questions also. Isn't it, Jeet?
Sir, I have one question that if I have a piece of semiconductor of normal silicon, and if I do a gradual increase in doping, like the equation of Y is equal to S, and what is the electric field of that piece of silicon?
Okay. So you have the expression. No, now I don't remember the exact expression. Okay. Okay, one second. So if you have a uniform semiconductor, it's very easy. Okay. But if you have first of all, let's understand this, okay, conceptually, and then we'll derive these expressions. You have a piece of semiconductor in which you are saying that here, let's assume that it's intrinsic, okay? Let's assume that here N equal to P equal to Ni. Okay, there's no doping intrinsic. Then we introduce a doping which is basically like this. Correct? Nd, let's call it, okay? Nd equal to Nd naught in plus X, right? Plus X into something, okay? Let's call it, we have to give some numbers here. Otherwise it becomes difficult. Well, yeah, you can assume what is the carrier concentration, right? I want X equal to, at this point, it is 10 power 10 electron hole pairs. At this point, I want 10 power 15, Nd equal to 10 power 15. Okay? This is what I want to make it. Okay? This is my doping concentration. Let's assume that it's X equal to 1, whatever units that is. At 0, X equal to 0, let me write it in this form, that's easier to understand. Nd naught, Nd 0 equal to 10 power 10, Nd equal to 10 power 15 at X equal to 1. Okay, units you take, meters, whatever, it doesn't matter. Now, what should happen in this scenario when you have an increasing doping concentration? Clearly, on this side, there are more of electrons, correct? Than this side, correct? There is a gradient in the concentration of electrons. Correct? There exists a gradient in concentration of electrons. Agreed?
Yes, sir.
So now, when you have such a gradient, electrons will diffuse from right to left. When electrons diffuse, there's going to be some exposed positive charge. Agreed? There will be larger amount of positive charge here and smaller amount of positive charge here. Okay? Because of which you will have an electric field. Okay? If I draw the space charge density, okay, there will be more density of charges here, plus, more dense, and then less dense, like that. Okay? So there's a gradient in the space density, space charge density, and because of it, there's an electric field. Jeet, agreed?
Yes, sir.
There's an electric field because there are electrons here. Electrons are moved all here. Okay? There's excess electrons, there's a balancing positive charge. Always the balance should be maintained between positive and negative charges. Okay?
Okay.
My son is saying it's okay. Yeah, good. All right. So, when you have such a scenario, should there be an electric field? Because there is variation, there's a space charge and there's a positive and negative charge, there's an electric field from positive to negative charge. What is the magnitude of this charge? I forgot the expression, but it was something like electric field equal to dNd by dx 1 over nd. Guys, is this correct? Can somebody check once? Or I can even do that. If you have a intro, let me just one moment open this up.
Sir, correct only.
There should be something else there, I think. I'm missing some term.
UND X by epsilon.
Q electric field. No, that's electric field in a PN junction, Nandana. You're completely confusing it. We're talking about electric field in this one. Diffusion.
Sir, KT by Q will be there.
There'll be KT by Q. That's what I'm missing, right?
Yeah.
Basically, electric, you can
Yeah, the
equate
form
the
is
diffusion.
1 by n into dn by dx.
Correct. D by dx. This is basically finally going to come out to be KT by Q and dnd by dx. Good. Okay, so this should not be there. There should be a KT by Q. How do I remember this? Well, there should also be 1 by nd, no?
1 by n also will be there. KT
Yeah,
by Q, 1 by
otherwise
n.
you're not balancing the charge.
Yes, correct. Yeah, 1 by n.
1 by nd should be there. 1 by nd, if you keep, basically this is taking care of the centimeter cube inverse. This is volts, and this is volts per centimeter. This is the expression. Okay. So now if you apply this, I mean, this actually can be derived. I mean, it's done in one of these lectures. You can go back and check. Essentially, what we are doing is we are talking of diffusion and the drift currents balancing out each other. And from the expression from the combination, at equilibrium, there is no net moment of charge. This current will be 0. So by substituting, you can actually derive this expression. Okay. Okay, we are not really doing that. Okay. But essentially, you can go back and take a look at the introductory chapters, non-equilibrium situations, and you will see this. Okay. Now, if you go back to this, our ND expression was ND equal to ND naught. So that is 10 power 10 plus 10 power 15 into, 10 power 15 into x. Okay. So if you do this, you get an electric field which is of the form, whatever, you know. It's kind of tricky here because you still get ND of x here. Electric field also is a function of position. Okay, into 10 power 15. This is what you get. Okay, Jit, if you took the expression ND to be equal to ND naught, this is probably the term that I solved in the lecture. If you have some expression like this, exponentially varying doping concentration, then you get a linear electric field. Okay, or constant electric field. Sorry, not linear, constant electric field. That is the problem that is probably solved if you go back and look at it. Where is this? There's a textbook problem which probably is solved somewhere.
Sir, in this case, it will have a drift component also or not?
That's a very good question. Why should there be a drift component at all? Right? There should be a drift component because there's an electric field. Diffusion is easy to understand, right? Because there is a concentration gradient in terms of ND. There's going to be a diffusion component. The drift component is because, so diffusion causes the electrons to move in which direction? In this doping concentration. Electrons move in negative x direction due to diffusion. Okay. What about due to drift? Yeah. Move in positive x direction due to drift. Correct? When you have balancing of these two things, these two forces, then you have steady state. Okay? Agreed?
Yes, sir.
Yeah. So that's why you get an electric field. All right?
Yes,
Just
sir.
don't
At
okay, don't
infinity time
Yes, sir.
in equilibrium.
okay.
Sorry?
Please
At
don't.
the infinite time is equal to infinity or infinite time, this piece of semiconductor in equilibrium or say in the condition like this diffusion.
Right,
It cannot be at infinite time. There has to be some kind of equilibrium established between the drift and the diffusion, and you will not have any more changes in the. If you look at dN by dx, right? Or there is no net current. Okay, let me call it like that. Okay, so if initially when there is a diffusion, is there a diffusion current? Of course, there will be some diffusion current for a short time, right? At time t equal to 0, you had this doping concentration. The diffusion starts happening, and then drift starts happening. And at some point, they reach a steady state, and there is no more change in the carrier concentrations. Okay? The net after some point, at some t equal to something. Okay, after some time, drift cancels diffusion, and semiconductor in steady state. There is no net current, no J net. J net equal to 0. Okay? Is that fine, Jit?
Yes, sir.
So only for some time it will flow initially. At time t equal to 0, you have created this concentration gradient or a doping gradient, and then for some time it will flow. After that it will stop.
Upside down and do like this. Put it upside down.
1 second. Nandana, can you just make note of this one? Just remind me tomorrow about this, okay?
Yes, sir.
Remind me about this idea of concentration, the current variation, okay?
Yes, sir.
Current variation as a function of time, and we'll discuss something about it. All right? Yeah. And probably we should think of any way of
We know this
doing,
also.
yeah. So the method of calculating this over as a function of time, if we can.
Yes,
The
yes,
drift and the
yes.
diffusion component, if we can do in time, that would be fantastic.
Sure, sure.
By the way, this is not for you guys. It's just internally we want to do certain things. Yeah. Any other questions? Yep.
The end.
Sir, I have another question that on a piece of silicon, I am putting the light source on the side of the semiconductor or piece of silicon, not the top of the semiconductor. What will be the current or equation or something
Okay.
else?
Okay. So first of all, for that, you need to solve what we call as minority carrier diffusion equation. MCTE, right? We called it minority carrier diffusion equation. And this is what you need to solve. right? What is this equation? Let's say an excess minority carrier is a D of delta, let's call it delta n-type semiconductor, delta P, okay, as a function of dt, sorry, first derivative should be equal to what? dp t square anything else, guys? Generation of P. What else is there? Anything else? Let's forget recombination or G minus R. Okay, that's this thing. Okay, this is my minority carrier diffusion equation. Agreed? This is what it is, correct? Oh yeah, sorry, I didn't put in the recombination.
It will have a drip component also or not?
Sorry, it will have a?
Drip component.
No, I mean, this is basically, wait a minute. Okay, so what we're saying is, this is an interesting question. Okay, now what will happen when you shine light?
Oh my God.
See, the problem you are saying is, we'll have silicon, let's take its n-type silicon, and I'm shining light from the left side. Okay, when I do this, I'm assuming that it's not penetrating inside, it's only at the interface. Electron EHPs created at the interface. Right? Now, this question is, will there be drift or diffusion current? Let's analyze. First of all, is there a concentration gradient? Let's assume that this is 10 power 15. Okay. And we are creating, let's assume that at the interface, this is creating EHP. EHP's concentration is basically 10 power 18. Okay. Uniformly, we created all across at the interface. Will there be a diffusion or not? Jit?
Might be diffusion due to the electron is moving on the other side, or it will excite the electron and after that sometime it will diffuse on the other side.
Okay, let me show you something. Okay, let me show you. Let's solve this equation. No? Let's solve this equation, and let's assume that we create continuously a steady state. No? Continuously, you're creating continuously EHPs, right? 10 power 18 EHPs, right? Are created at x equal to 0. We did this situation. Now, what will happen? Are we at equilibrium? Let's think about the carrier concentrations. Let's plot carrier concentrations as a function of it's a logarithmic scale. Okay, this is log. So first of all, you have n-type semiconductor. So you have n0 equal to 10 power 15. There is a p0 equal to, this is equilibrium carrier density, right? 10 power 5. Agreed? Now, I'm creating it suddenly here 10 power 18 electrons, basically n equal to p, right? Much larger carrier concentration. Is this in equilibrium? Well, the question to check is n into p equal to how much? N into p equal to 10 power 18 into 10 power 18. That's equal to 10 power 32 is much, much greater than 10 power 20. Ni square, right? It's not n, it's much greater than Ni square, so it is not in equilibrium. Equilibrium. Okay. Now, if you have such a scenario, let's assume that there is no variation. Okay, there is no time dependence. So in this guy goes to 0.
Okay.
Okay. So what will happen now? The equation reduces, and also there is no, sorry, this is a recombination. So then we don't need this. Okay. So this guy here goes to 0, and inside the semiconductor there is no generation. So basically your equation becomes this. Okay. Your minority carrier diffusion equation becomes dp d square delta p by dx square equal to delta p divided by tau p. Okay. So this equation turns out to be equal to, if you remember, we know that LP equal to root of d tau, dp tau p. Okay. So this is equal to something is off, guys. What is off? Something is off. 1 second, let me check. Okay, fine. Let's see. So
At the end.
this is LP square d square delta p divided by dx square equal to delta p. What will be solution for this? What will be the solution of this equation?
Some kind of exponential function due to this is a second order differential equation. So
There's something we are missing in this. Just 1 second. That's it. Okay, fine. We're not missing anything. All right. Okay. So basically, the solution is going to be some kind of a second order differential. It's a second order differential equation. So we can guess this delta p of x is going to be a times exponential minus x by lp plus b times exponential x by lp. Okay. This is going to be the differential equation solution. So if you solve this, first of all, no, this is a guess, right? This is a guess solution. Just by inspection, I know that my minority carrier density cannot increase as a function of x. It cannot be like this. Okay. So this solution cannot exist because this should go to 0, because at x equal to infinity, okay, delta p equal to 0. That much we know for sure. If you go far away from the interface, nothing much happens. Okay, only this is a solution. Okay, so now so the minority carrier density, what happens is the excess minority carrier density, it reduces as a function of x. This is what this is telling us. Okay, so if you shine light at the interface, you have large minority, large concentration, okay, of 10 power 18, and they decay as a function of x, and you reach. This is basically exponential minus x by lp. Okay. Similarly, the majority carrier concentration n, right, will also decay. They will recombine essentially. This is n of x. This is p of x. Okay. So basically, you have a situation. Actually, I didn't even show you what happens with the majority carriers, but essentially they recombine. You get the drift, right? So this is a recombination that's happening, and away from the interface, you have this going back to equilibrium. This is the decay of the minority carrier concentration as a function of x. All right.
yes, sir.
So if you shine light, and how much distance does it take? It takes the distance of LP, a few diffusion lengths. Okay. After a few diffusion lengths, LPs, delta P is going to be 0. How much is LP? LP is going to be root of dp tau p. dp is basically roughly of the order of 10 centimeters square per second. Tau p could be roughly of the order of 10 nanoseconds. You take it and you solve for it. You get the expression. Okay. Each semiconductor will have a different minority carrier diffusion, that's depending on the doping and so on. All right. Yeah. Let me move on. Any other questions? I hope I clarified, Jeet. I'm glad, guys. I mean, I didn't know that there were so many questions. We'll do it again. When is a good time? Let's do one more session very soon, next week, maybe early next week. When is a good time for all of you? Can we do it at the same time? On a
Can you suggest?
I'm happy to do it on a Saturday morning if you want. Saturday morning session will work for most of you who are here. Let's say
Sir.
Saturday morning around 11 o'clock or 10:30.
Sir, this is the right time for me.
This is the right time for you. Okay.
Sir, can you suggest for
Sorry?
simplest book, sir?
Sorry?
One. Sir, simplest book. Simple book, sir. About this matter.
I'm sorry, I didn't understand what you're saying.
A simple book, something you want to study.
Simple book. I don't know. See, every book will cover some aspects. I like semiconductor device fundamentals from PNA. But that you have to skip some sections, okay? One of the good books I feel is Semiconductor Device Fundamentals by RF PRA. And I mean, Streetman Banerjee is there, Neiman is there. Every book is good. You should not read only one book. You should read 2-3 books simultaneously. Don't read page to page, sentence by sentence. Try to understand the broad concepts. It's better. Okay? Yeah. Anything else, guys?
Sir, there's a question in assignment 7 that for a p-type MOS capacitor, increasing the acceptor doping concentration will increase or decrease the threshold voltage. Sir, so if it is a p-type MOS, then the substrate should be of n-type.
Correct.
So how can it I think the correct answer is increase the threshold voltage. So I'm just confused about it, how this is happening.
I'll suggest one thing, okay? So let me not answer it directly. Have you tried NanoHub? I have showed you some of these examples, right, in NanoHub?
Yes, sir.
So try to put in the concentrations in NanoHub, okay?
Okay, sir.
And try to see what happens to each parameter. The challenge is, it's not one parameter that depends, okay? Generally, when you increase the doping concentration, you tend to increase the threshold voltage. But put in the concentrations, because finally, what you'll have to look for is what is happening to C depletion. Okay. Take a look, put in the NanoHub simulator and just try to observe what is happening. That will be a better way of dealing with it. Okay.
Okay.
Yeah. And another way of looking at it is, if you increase doping concentration, what is your inversion charge threshold that you need to reach? For example, you have a 10 power 15 doping, okay, initially, p-type. Okay?
Okay,
so PMOSFET. If you PMOSFET, it will be ND, right? Okay? And then you consider ND equal to 10 power 18.
So, but it's the acceptor doping concentration which is increasing.
Okay, so you're talking of NMOS device.
So the question is PMOS type, P-type MOS capacitor and increasing the acceptor doping.
It cannot be P-type. Can somebody flash that assignment, please? We'll call it either, PMOS. When we say PMOS, we're talking of N-type doping.
Yes, sir, that's the confusion I'm having. So NMOS,
P-type substrate. Yeah, can somebody just, one of the TAs can just flash that for me, please? Assignment 7. Yeah?
Yeah, it's a PMOS. Then if we are increasing the doping concentration, how the threshold voltage will change?
Okay. So it's a PMOS device, so it should be N-type doping, right?
So, but it says accepted doping. So,
Oh, it says accepted doping. I'm sorry, I don't have access to this.
Sir, can I share?
Yeah, please do. Do I need to stop sharing for that?
I have no access to share, sir. I can share in the WhatsApp too.
Yeah, please just share it in WhatsApp. I'll open it here.
Uploaded.
Yes, I have shared.
Yeah, just one second. For a P-type MOS capacitor. Acha. It's a little bit, I mean, it's just a terminology issue. Yeah. P-type MOS capacitor increasing acceptor. When we say PMOS, we are talking of ND. Okay? Not NA. Guys, we'll have to check this once. It can be a little bit confusing. Okay? TS, please make note of this and just remove it from the evaluation. Yeah.
A few other questions are there in the Excel sheet.
Okay, what are the quickly short ones? Because I have the other session also now at 7:30. Okay? Quickly tell me the questions.
Like, since in the energy band gap, there cannot be energy levels. Then how Fermi energy levels are existing in the energy band gap?
Say Fermi energy level is a computational thing. It is not a real level, right? So it's basically a balance of, it's a kind of it's a probability distribution, right?
Sir, it is available in YouTube.
Sorry?
Sir, please can please upload it, sir. Recorded.
I didn't follow the question.
Sir, please record.
Okay, so I'm just trying to explain this concept. I'm explaining the concept here. So basically, you'll have two things. Okay, the carrier concentration is dependent on two factors. One is the density of states, and the other is Fermi distribution, right? The probability of occupation of energy. So the total is basically, okay, the integral is what determines this. Now, for a simple, let's say, intrinsic semiconductor, so your probability of occupation is a Fermi function that we know. F of E is equal to 1 by 1 plus exponential something. Right? This is your Fermi function. Now, what happens is at an intrinsic semiconductor, you have equal number of electrons and holes here. If you compute this, if you do this, this is like a electron density that exists in a intrinsic semiconductor, equal number of, this is basically N and this is like P. Why is the shape coming like this? Initially increasing and then coming down. Why is this coming like this? Well, if you go away from the band edge, the density of states increases, but the Fermi probability will decrease. Okay, so combination of it slightly away from the band edge is where you'll have the peak concentration. After that, it reduces significantly. Okay. Now, if you have a situation like this where there is equal probability of electrons and holes, therefore electrons in the conduction band and holes in the valence band, you have basically, what is the probability of finding electrons here? F of E. Okay, let's skip that part of it. Let's look at it. So since there is equal probability of finding electrons and holes here, your Fermi level is going to be somewhere in the middle of the gap. Okay, but this is a regular intrinsic semiconductor. But if you move to an N-type semiconductor, you have a lot more electrons than the holes in the valence band. Okay, there are N is large in conduction band, P is small. Okay. So in this case, what's happening is you have more probability of finding electrons closer to the conduction band. That's why we say that the EF is closer to the conduction band. EF of N type. Okay. If you have the opposite scenario where there are a lot of holes in the valence band and a few electrons in the conduction band, your EF will be closer to the valence band. Okay. I will ask you to go and take a look at these diagrams. They're probably on the slides anyway. Okay. So what is the probability of finding an electron in the conduction band? Okay. You try to look at that. You can even do this. What is the probability of finding an electron at EC? Of finding electron at EC, at the conduction band edge. What will this be? This will simply, f of E we know, right? F of E is some expression like this. 1 by 1 plus exponential E minus EF by KT, correct? At EC, what will be the probability? Okay. So at EC, f of EC will be 1 by 1 plus exponential EC minus EF by KT. What is the probability of finding holes? Of finding holes at EV. So what you can write it off as 1 minus the probability of finding electrons is 1 of f of EV, and then 1 minus that will give you the probability of finding holes. Okay, this will be 1 minus 1 by 1 plus exponential EV minus EF by KT. Now these probabilities are equal. So if you solve for it, you will see that EF equal to EV plus EC by 2, essentially. Okay. I think I have done this in the lectures. Please go back and see. You will see this easily. Okay. Next one.
Some question related to assignment is there, sir? Like 3 questions are there.
Let's take it up.
Next session.
Let's look at it tomorrow, Nandana, because we cannot, because I have to go for the other
Yes, sir.
live session in 2 minutes. Okay, let's take care of it tomorrow and we'll answer it on the forum. Okay.
Okay.
Sir, one guy is asking about the Spark project.
Huh?
Indo-Taiwan.
Who is asking?
His name is Ranadhir from Mysore.
In
NI
which
Mysore.
one? In which one? In this
Yeah,
lecture?
here only in the Excel sheet he mentioned.
What does he want to know about Spark project?
I don't know. He didn't mention much. I think he's interested and he wanted to. Will it be or somewhere written when it will be conducted, something like that.
We will do that. We'll do it soon. Okay. We're working on it. Yeah. We might have a call sometime towards October or something. November, we might have a session. The first phase 1. Okay. All right, guys. I'm sorry I have to log out because I have to conduct another live session for a different course. It's nice to meet you all. And I will plan to do one more session. So we agree that similar time is good. So maybe next Monday we'll do it again. Okay. Yeah. Same time, I'll try to have one more session next Monday. Okay. In the meanwhile, if you want it, yeah, just send emails, send questions. We'll conduct it. Okay. All right. Thank you, guys. I'm sorry I don't have more time right now. We'll meet you again next time. Thank you.
Thank you, sir.